No, thanks. Appreciate it. Thank you.
So the first thing that's going to be on the test is computer history matching. So that's going to be off my slides. So one of them might be ENIAC, and the match would be one of the first all-electronic computers. And of course, every time I say the first thing that's going to be on the test, somebody else walks in.
Start over.
Start over.
Hit reset.
At least you guys have legitimate reasons. Thing called a job, you know. My 10 students come wandering in 20 minutes after class begins. Oh, I couldn't get up this morning. The class at 9:40. It's not that hard to wake up. Anyway, so for the third time, the first thing that's going to be on the test is going to be computer history.
Off your slide.
Off my slides. And they're going to be matching. So, the example I was going to give was ENIAC, one of the first all-electronic computers. I'm going to have to drop the first, because it used to be the first, but now there's proof that a computer in England was the first all-electronic computer. They just had it top secret until this past year.
Wow.
Okay, the second part is going to be number systems. So this is going to be decimal hex binary conversion. No calculators. Very similar to how we did it in 3232. It's a table, fill it in, sort of thing. There might be a few additional questions, so be able to identify, for example, how would you determine if any of those binary values are could be considered negative? What do you look at?
The most significant bit?
Most significant bit. If it's a 1, it's a negative number. How can you tell if it's a printable ASCII character? Characters over 20, I believe it's 20 hex are printable. 20 hex to 7F are all printable characters. Oh, excuse me, 7E. 7F is delete key. Then, hey, what's next on my list?
So there's no, it's just decimal, hex, binary, no octal, right?
Okay. In this class,
Okay,
we will almost never use octal.
right.
The last time I saw a computer that used octal was a 1980s-ish computer. You should still know octal because the only place still using octal, there's 2 places I know of. PLCs still use octal from time to time, and the Linux operating system uses octal for identifying read, write, and execute permissions for a file. Are the only 2 places I've ever seen octal used now. So I am not including octal on the sheet. You should know it, but is it imperative for this class? No, so I'm not going to test on it.
Okay.
And you should have learned it from 3232. I'm sort of typing as I say here, so I remember what I say. I haven't made up the test completely. I sort of know what I want to put on it, but I haven't made up the test yet, so I don't want to put in anything I didn't warn you about. There will be something on internal architecture. So what's inside a CPU? How does it talk to memory? So, for example, what are the components of a CPU? Name one. Clock, I would accept a clock, yeah.
Input, output. Or that's not CPU.
That's not really CPU.
Bus.
Uh, nope, because that comes out.
RAM.
Control,
RAM. Is it?
not really part of.
That's a
the-
microcontroller. Oh, okay.
If it's inside a microcontroller, but
Microcontroller.
not inside the CPU, inside the microcontroller.
Okay.
What was it? I didn't
Talk
hear.
about data bus, isn't it?
No, that goes outside the CPU as well. ALU is right. I did not hear him say it. BIU, bus interface unit. The buses come out, but the bus interface unit that controls them is internal. What else?
General registers.
General registers, you better say that. You just asked a question out in my office a few minutes ago. You better say that. What else? Flags.
What is it?
The flag.
Flag. Okay.
So when the ALU is done with its calculation, those are the ones that say conditions of the answer. Is it zero? Is it negative? Is it positive? Etc. So that's pretty much so here this is for an 8086, but ALU, the control system, the bus interface is up here, the general purpose registers, the flags, and the bus interface unit, and they call this the execution unit, but I consider it part of the control system. I will not get too detailed in that because basically what's in that Scott processor video is about the level I want you guys to understand it. There might be some questions about address and data bus. So for example, given this data sheet for a memory IC, I want to retrieve this memory location, what would you have to do to retrieve the value?
Oh.
So what did you have to do in experiment number 1, 2? Actually, either one would work because one, you were retrieving stuff from an EEPROM. So what did you have to do to retrieve information from an EEPROM? Better go back and look.
You had to set those pins or those pins. Those yeah, the pins.
What pins? What pins? What do we call them? We have to set the address. So you have to put the binary pattern on the address pins to retrieve the value we want. What else do we have to do? Yep, that was in there. What else do we have to do? Read and write data, especially if it's RAM. That direction matters. What else? No, there's no registers in memory, there's memory in memory. So selecting the memory location is putting the address on the address bus.
Get something flip-flop, stolen data.
That would be the rewrite, if it was a RAM. What's the last one we have to do? Nope. Again, it's memory, not registers. What happened when you did the end of this lab?
We have to verify that
What happened when you did these steps? What happened? That's why I don't want to wait until after spring break for this test.
we made an address and put that in, and at the end, it went from writing data into the memory to us.
You're thinking lab 3, and you're not thinking wrong, but that was rewrite. What happened when you were dealing with these pins?
You got something weird.
You got something weird.
I got nothing.
You got what?
I don't know, maybe it was nothing.
Maybe it was nothing?
Yeah. Then nothing happened. I got floated.
You got a float. Why is float so important? Why is float so important? That one might just have to do. Yeah, that one's just gonna have to do. Not my favorite, but hey, there we go. Say other is another RAM. Why is float so important?
In case you want to, now we talking about. Because I can think about increasing memory and having an extra big cool, but I think this is what we're talking about.
It's part of that.
What about
Because it definitely does, if I want to add more memory, float really matters. If I have one memory IC, float doesn't matter that much. But if I have multiple ICs, float matters. Why? We talked about this. It was even one of the questions in the lab, I think. Okay. RAM, ROM, and I'm calling other another RAM. What does an arrow going out only mean? It's an output or an input to the RAM. So this is an output from here to the RAM to set the address. What does the double arrow here mean?
It's a
Input and output. Okay, so if these can be inputs and outputs, let's say the ROM and the RAM both want to output to the CPU. What would happen if both of them are turned on at the same time?
Float? That's what you mean?
Nope. It has something to do with float. float is the solution to the problem, but what would be the problem if both the RAM and the ROM put something onto the data bus to the CPU at the same time?
Oh, well, they will interfere with each other.
They'd interfere with each other.
Right.
Because I might have a 1 and a 0 on the same line, a 5 volt and a ground, I have a short circuit. Float and that output enable or chip enable function says I'm shutting off my output pins so somebody else can use my data bus. If you don't have the ability to shut off the output pins, make them floats, you would have bus contention, short circuits on the bus, and a computer won't work. So you have to make sure you chip enable the one you want and disable the ones you don't want to talk to, so only one of them is outputting to the bus at the same time. So that's the reason why the output enable is so important. So that's what these OE and CE pins were about in this lab, was they put it in a float condition so some other memory chip can use the bus. You only have one thing actually talking to the bus at a time. I might ask you a question about how does an instruction get executed? What steps does the CPU take to execute an instruction from memory? So this is the Scott CPU sort of idea. What's the first thing that has to happen for a CPU to execute an instruction?
It has to know where to go.
Know where to start.
Sort of vague, but you're barking up the right tree. What do you need to know first?
Where is the instruction located?
Where's the instruction located? Okay, I'll grant you that one. Okay, after you know where the instruction is, what do you do?
Find out what type of instruction it is.
Hmm?
Find out what type of instruction it is.
Does it have to do with registers? Or no?
Nope. Baby steps. You know where it is. What do you have to do next? Retrieve it. You have to go get that instruction.
Fetch. Yeah.
Fetch.
Yeah.
So you got to fetch the instruction. Then what happens?
You have to read it.
Break if it's
Sort of. Okay. So the bus interface unit has to know where it is, retrieve it. That's step one. Retrieve the instruction. Then what? What part of the CPU kicks in now? I have the instruction.
This is send it
The control. It does what?
Determines what type. Send it to other or somewhere else.
The control system.
Prepare and edit.
Yeah, keep going, keep going. You're barking up the right tree. It has to set up the rest of the CPU to execute the instruction. If it has to set up the ALU, it has to set up the ALU in a particular fashion. If I'm doing an add, it has to tell the ALU to do the instruction. It has to say what registers are going to be used. So it sets up the CPU to get the right registers in the right place and sets up the ALU to execute the instruction. So it's the setup to execute the instruction. Then what's next? Baby steps. What's next? We retrieve it. We figure out how to execute it. What's next?
I guess once you figure out the execute,
Execute it. What's next? Last one.
stop it.
I don't know what you mean by stop it, but
Well, when you execute, when you know it's
Repeat again.
huh?
Store it.
Store it. Do something with the answer. Sometimes it's just change the flags. I don't care how to store it, but other times you have to store the answer. So fetch, set up, execute, store the answer. That's it. That was all in the Scott video. We haven't watched it in a while. You might want to watch that one again, but those execution cycles are there. So that's internal architecture. I think those are most of the questions I will ask on that one. Or similar. What's the difference between machine language and assembly language? And you can't answer. We were just talking about it in my office. So, what's the difference between the two?
Assembly language is close to machine language, but still difficult to read it.
Okay, I'll grant you that. So assembly language is more human readable. What about machine language?
It's just the binary.
It's the binary. The more readable, we usually refer to those as mnemonics or opcodes. That's like that LDI, load immediate. I don't have to look up what LDI stands for. I remember it because it makes a little bit of sense. Add is add. JMP is jump. BRC is branch. So it's a mnemonic sort of helper. It's very close to machine language, but it still has to go from the text we type into the ones and zeros, the hex that we put into the memory. So it's the difference between the list file and the bin file. In experiment number, I want to say that was number 3 or 4.
So when you mention CPU, you talking about microprocessor,
Yes.
and that's different from microcontroller.
CPU microprocessor is just the CPU. The ALU, bus interface unit, the registers, etc. in one chip. A microcontroller has an entire computer on a chip. So it has memory. It has RAM and ROM. Those usually aren't included in the CPU.
Okay.
I will ask you to do a conversion from machine language, assembly language to machine language, or machine language to assembly language. I will give you the standard sheets. So I will give you, so the RRs and KKs, you have a reference for those. I might give you like 4 different instruction sheets and only ask you about one of them or something like that, but just to make sure you understand what you're looking at a little bit. Then, the last part of the test is going to be handing the rest of it, then be given a, go write this. We're in the lab, we might as well do a little bit of C programming. The program will be up to, but not including input. So it's going to be a strictly output. Use the pins I tell you to use to do the following sort of program. I'm not going to make it too hard. It's not going to be A to D. It is not going to be input. It's going to be output only. So know how to set up an output register. Know how to figure out from, if I give you a pin or multiple pins, you know how to set up those pins correctly for output. You know how to wire up to the pin I tell you to, and then do whatever I tell you to do. But that's going to be the programming part of the test. I'm going to take it easy on you on the programming part this time because two people are a little bit behind still, haven't caught up yet. So, but everybody did those labs. So it's going to be somewhere, definitely not as complex as the stepper motor, but using output only. Now, I stopped typing, I probably should have. Right. Computer history, number system, CPU architecture, ASM machine language, C programming out. Basically, that ends up being anything before anything there and above. So up to February 7th, but not including February 12th, is the material I'm going to try to keep it to. You might have to do a loop. Etc. When you're doing the programming, you have full access to the internet. So if you need to look something up in C, you can do that. I'm not going to sit there and watch over your shoulder and see what you're looking up on the internet.
Can I test it to see if it works first?
What?
Can I test it and put it to see if it works? Or...
Oh, this is, at the end, I want the code, I want a demo.
Okay.
So, no, it's not. In some ways, I believe on, handing you an exam and say write the code and you don't get to test it to see how many errors you make. But I might pull that toward the end of the semester. I'm not going to pull it now because some of you are still remembering what you learned in C. So, and really and truly, at a company, your boss is going to look over your shoulder. Ha, you missed a semicolon. But he's going to yell at you if you compile it 20 times, it never compiles, and then you hand it in and say, I'm done, and it doesn't work. That's when he's going to be pissed off at you. Or if it takes way too long. So now's your opportunity to ask questions. Please don't say, tell me exactly what's going to be on the test.
Can you go over the OE again and
Hmm?
the float? The float. And
The float. Okay. I'm gonna do it. Oh my word! I don't have any pens. Oh no! I gotta go get a marker.
Are you shitting me? Hey, I gave you a pin earlier. I gave you a pin before the boss concert.
No, dude. No.
How was that all?
The boss concert?
Yeah.
Pretty fun. It was pretty dope. It was. So there's. I've never been to that place before.
Yeah.
And then so it's like Hazelwood almost like one room, I guess. More. But then next to that is an 8-4 line, 18-8-4 line, or whatever it's on this line.
Yeah.
Which was like half. But and it was small. It was a lot smaller than I expected. But it sold out. It wasn't like too crowded or anything.
Bro, literally that night, I found out about him that day. And then I
It was pretty good.
Googled it. And I was like, wait, boss, I'm doing this. I was like, are you shitting me?
Yeah, somebody else was like, how do you spell that?
Dude, I was blown away. It was bizarre. I was like, so like, I could have seen him instead of just hearing him. Like,
Be on the internet.
Okay. So I have two 1-bit memory locations, M0 and M1. I have two tri-state buffers. And memory 0, I have a 1, and memory 1, I have a 0. Just for kids. I have two chip enable lines, one for memory 0, one for memory 1. Right now, if both of these are 0, both of these act like open switches. So my output D0 is just a float. If I activate one of my chip enables, excuse me, that should have been a 1 and a 1. It's active low, sorry. The bar says active low, remember? So right now they're open switches. If I make one of these a 0, this closes this switch and puts this output over here. Because this one is still disabled, this one is an open switch, this one is a closed switch, this one goes to here, I have no problem. If I close this one too, then I have what they call a bus contention, because both of these would be on, so they'd both be closed switches. I'd have a 1 coming out of here, a 0 coming out of here, which means D0 short circuits and things start to fry. But by being able to control which one gets to the output, I avoid that. Now, if I multiply this out by every one of the bits, 8 bits and 8 bits, now I'm turning all 8 on and all 8 off at the same time. So I'm only allowing the output of one of the memory ICs to get on the data bus to talk to the CPU at a time. If I don't do that, I'm constantly going to be hitting these 1s and 0s being on the line at the same time. And as we saw in digital, anytime you hook up two outputs together, it's bad news for the circuit. But with the tri-state buffer, I can electronically control which one is on the bus at any one time. The rest of them are disconnected. It acts like an open switch, so only one memory IC can be on the bus at any time. Does that make some sense?
Yes. So could you relate that to any like labs we did though? Or any-
Other than, the only time we really did it was when we removed the output, when we turned off the output of the prom. And the next question was, how can you hook two proms together? And the next address line, anytime you want to double memory in a computer, you have to add one more address line. So what the last question was, how can you double the amount of memory? It was add one more address line and tie the address line to the output enable. One directly and one through a NOT gate. So only one of them is on at a time. So if I have two memory ICs here and here, they're both connected to the data bus. So they're both connected to the same data bus. That's all 8 lines. But if I do a chip enable, make this a whatever. If this is low, this one turns on, this one gets a 1, so this one turns off. So this one's talking to the data bus, this one isn't. If this is a 1, then this turns off, this one goes through an inverter, 0 here, so this one turns on and it talks to the bus. But only one of them is allowed to talk to the bus. If you want to add more memory, you just have to make that more complicated and add another address bus and then make logic so only one IC gets a low at a time. Other questions?
I don't know if the character was printable.
How do you know if a character is printable? Well, the easiest way to know if a character is printable you have the handy dandy little ASCII table. Space is printable, but it's not visible. But anything above hex 20 to hex 7E are all printable characters. A space is printable, it has an effect on the screen. All these guys, null has no effect because there's no characters. All these, let's see, those are just a bunch of old things we don't even use anymore. Yeah, you can make the computer beep within character 07, but nobody does it anymore. Tab does have an effect. You could argue that's a printable character, but you don't see it print anything until another character is printed. Carriage return, line feed have a effect on the output, but you don't see it until the next character is printed. And the rest of these are all what they call control characters. So really, 20 through E7 and delete, you could argue, is not printable either. It just has an effect on the output. Other questions? And I'm still debating. Depending on the type of question I ask, I might include the ASCII table, I might not. If you need it, I'm going to put it in. I might ask a question, in all the numbers you converted, are any which ones are a printable character, and if so, which character? And then I'll give you the ASCII table because I wouldn't have it memorized either. I will ask you to identify negative numbers. I will not ask you to convert what they are. So I'm not going to ask you to do two's complement. I'm just going to say what numbers of the above are negative, could be negative values if they're defined as an as a sign care, for example. So if these are signed as a sign care, which ones would be a negative value? Would be a valid question. And all that means is a care is 8 bits, and the top bit is the negative sign. So if it's turned on, it's negative.
So if it's most significant bit is 1.
Most significant bit is a 1, it's a negative. If it's a 0, then it's
So that's what
negative.
signed and unsigned is?
Yeah. Yeah, it's just that when you say it's a sign or don't say it's unsigned is more like it. You have to declare unsigned. It defaults as signed. But when it's a signed value, they steal the top bit to be the negative sign. I'm not 100%, I think I talked about this, but I want to make sure because there might be a question on the test on that. If I asked you to identify the most significant bit, I think everybody knows what I'm talking about, right? I hope. But if I asked for the least significant byte, would you know what I'm talking about?
Mine is.
Yeah. Just talk about it, I think, in the office.
So if I gave you, here we go again. If I gave you if I gave you that and said, draw a rectangle around the least significant byte, what would you be drawing a square around or a rectangle around?
It'd definitely be on the right side. But
Right side, okay. So we're starting there, okay.
Could be 8 bit.
What? Okay, I think I see where you're going. Tell me where to stop.
Stop.
No, to
What is that?
That's-
Nibble.
That's the least significant nibble. Okay?
There you go, right there.
That's the least significant byte. Now, if I ask you for the third, so that would be the least significant byte. If I asked you for the third nibble from the right, what would it be?
A little 4 more, I think.
The next 4 more?
Yeah.
That's the third nibble. And if I asked you to do the most significant word, 16 bits, so it's the entire thing, and it doesn't matter whether I named it most significant or least significant, it's the entire thing. In our processor, 8 bits is a byte, 2 bytes is a word. In some processors, that does change.
That'd be a question.
No. But this will be indicate this by drawing a circle around it, indicate this by drawing a square around it, indicate this by putting a line under it. Knew there was one I forgot.
So 2 bytes make a word.
2 bytes make a word in our processor.
So basically, reading from your PowerPoint, we should be fine, right? Like not from your side.
PowerPoints for definitely the computer history, the number system stuff you might have to review. Internal architecture, I'd look over that chapter and the stock processor. The opcodes that look over that lab where we did that. I'd definitely be looking at your labs for the memory questions as well. The C program, look over your labs up to the stepper motor. If you got a good grasp of the stepper motor, that would be good. I don't think I'm going to ask any thing outside of the program on setup registers. On future tests, I might say, this is not on this test, this is on the next test, but the next test might be something to the effect of, you want to read the A to D on pin number 3 manually at this clock rate. What registers would have to be set up the registers to do all that. So you'd have to set up AD MUX, ADC, PA, or whatever it is. I'm still learning these memorizing these ones too. But then you'd have to tell me what binary pattern would have to go in each one. That's not on this test. The only one that you're going to be asked is, here's a program, write it. You have to use my pins, which means you have to be able to set up the pins to an output the way I define it, and that'd be in the program.
Is that like just a little review? When you set up a register as an output, that's what you put, whatever register you want, DDRB equal, for example, if I want it in binary 0B and then 000, for example, or 1111, that's
Yes.
what you mean with it?
Yes. So you'd have to put the ones in the right place to set up the output pins
The
to
output
be
pin.
outputs.
Right.
And I will probably specify, leave all other pins as inputs. So you have to differentiate ones and zeros. You can't just do 0FF on DDR or whatever and say, oh, they're all outputs, I don't care, you know. No, I'm not going to allow you to do that. I'm going to have you put in the binary pattern.
Special pin.
I'm still debating whether to put it in that you have to use the pin names. I might leave that for the next test. I know some of you are still trying to get a grasp of that, so I might say you can use binary patterns. Actually, let's just say that and be done with it. I'll let you use binary patterns so you can set up DDR blank 0x or 0b 111000 whatever. You don't have to use the ands, the orders, the shifts, and all that for this test. Next test. And I'm sure if I contradict myself on the test, you will remind me. But you said. I know he's recording, so he's going to have proof. What else?
Because I know we're going to repeat fast and all that, but a register phone sending me like some machine names. I try to make it show. now I put it on my lab as a reference, a chart. Just use plain.
Okay, I'm just gonna pull an instruction up. Here's a logical and. So we're gonna do a logical and. I just have to do a little bit of checking here. I want to convert. And R 27, R 15. I'm just pulling that out of minute. So I want to convert that to hex. This stays. I can't do a thing with that. 0010 has to be there. So I have the hex value of 2 here. For this one, I'm going to have these 2 digits, but now I've got to do R and D. Now in this case, I have R here and R. This is my least significant bit. This is my most significant bit of my register, the second one in my list, which is R15. So, to be 15, I do not need a 16, so that's going to be a 0. Then 15 is all 1s, so this becomes an F. I still have this 0 here, F. That gives me the 15, the 27. I need a 16. This is my 16 bit. So 27 minus 16, I still have 11. I need an 8 and 3 more. So now I have 1011. That is 11. That is a B. And now I have a 1 here. So the machine language is 21BF, and it would be stored in memory BF21. Remember, we have to flip them around if we're storing in memory. I'm probably going to let you get away with just that.
And you always subtract from 27? You always subtract from 27?
Always subtract.
Like here, you say 27 minus 16?
Oh, I'm just, that's the way I'm doing binary conversion.
Oh, okay.
I'm converting 27 to binary. I use the 16, which is this bit. So I subtract that, I'm left with 11. Then I convert 11 to binary there.
So basically, the 15 you have to make it in binary, and then the
Yes.
20.
So
Okay.
really,
So you
truly,
take
the
okay.
15, 0, 1, 1, 1, 1.
Okay, for example, all right.
0 is here, 1, 1, 1, 1 here.
Okay, and then
For the 27, it's 1. So I don't have to do it again. 1, 0, 1, 1 is 27. And so I use the 1 here, and then the 1, 1, or 1, 0, 1, 1 there.
Okay, so always whatever come, the second one, like here 27, 15, the second one is always will be the R's, and the first one will be the D's.
You have to look at this sheet to see what it is. You see here it says and RD, RR. So
Oh,
this
okay,
D
okay.
is this D and this D. This R is there and
Oh,
there.
okay.
That's how it's splitting that
Gotcha.
up.
Oh, okay, I see. So you look at over there.
So
and
this
you-
is just a roadmap to
Right.
say this is how the bits are broken up to come up with the machine.
So maybe
language.
another one, it will be, for example, RRRD, and then you choose the RR on the first one, which is 27, for example.
Mhm.
Okay, I got you. Okay.
So any one of these opcodes Now this one is a branch.
Okay. So,
Starts out with this, but now it's got a bunch of there's 0, 1, and then a whole bunch of K's, and then 0, 0, 0, 0. So the K is a 2's complemented, negative 64 to positive 63. Those are my rules. I can't break those rules.
okay.
What this is, what a branch does, and I probably shouldn't have used the branch example, but I did, so now I have to
So it
explain
won't be on the test, the branch.
The
example.
branch basically is, we have something called the program counter in the CPU that points to the memory location of the next instruction. The branch changes that program counter to go backwards or forwards in memory to skip over instructions. So you're coming along and you see a branch and it tells you to go forward 63 memory locations. You jump over 63 memory locations to read the next instruction. That's why it's a plus minus counter, is to jump over or jump backwards in your program over memory locations.
Are you going to have any branches on the test?
No.
Oh, okay.
I'm probably going to stick to the ones you saw in Lab 3,
Like
LDI, and out.
Okay, yeah.
We're trying to get this class away from machine language. The only reason I'm leaving a little machine language in this course is so if you ever have to do machine language, you've seen this chart once before, and you understand the bits sort of decide what gets turned on, and to make you understand how programs get into memory.
Right. That's why when I was reading the first two chapters,
Right.
I'm confused a little
Right.
bit.
And chapter 3 will be even worse because that I think is 100% machine language.
Okay.
Chapter 4 is machine language for I/O, if I remember correctly.
Chapter 4 is an input output.
Right.
So
Read the output section of that chapter and you're okay.
okay. So do you advise me to skip the chapter 3 or just skip?
Really and truly, I find chapter 3 fascinating, but is it going to be a lot of testable material? No.
Okay.
If you understand this, I'm happy with what you know out of chapter 3.
Okay.
And my apologies for having chapter 3 in the course outline online, where I meant chapter 4. If you notice a change today, I realized I goofed.
1, 2 is cool because it starts with the basics.
Right.
But 3 is...
Three is, if you're getting into the machine language and you're going to do machine language programming, chapter 3 is really, really important.
Okay.
But I want to move to high level because most people now are not programming in machine language anymore. There's only two industries that I know of that really do machine language. Video games, because machine language is very fast, so I can program just what I need, so it makes my game smoother, makes the action of the game smoother. The other one is high-speed control. So the military rocket guidance systems still might use machine language because you program exactly what you need and there's no extra wasted time before it makes the next decision. But what they usually do even on those is they write a C program, they compile it, and then they go into the C code, the compiled code, and get rid of extra garbage that the C compiler adds. So they call that code optimization. We're not going to get, I know master's students who can't do code optimization. As a matter of fact, I probably only know of like 3 people who do code optimization. One of them is a video game programmer right now, and who's a former EEC student here, but he actually went to video gaming school and wrote video games. A guy I used to work with could probably do code optimization, but I'm assuming he's passed away, but I don't know for sure. But last I heard, he jumped out of a perfectly good airplane and his parachute didn't open, and he was in a hospital for in a coma. So I'm assuming, and that was decades ago. So I'm assuming he's probably no longer with us. And I'm trying to think of the third, but right now it's not coming to me. But it's a very sought after skill. You can make a lot of money with code optimization, but you really, I don't think I could come close, but it's still above my pay grade. If I do throw a different one at you, it will be an easy one to understand. I might throw, like and was easy to understand, or at least I hope so. Add probably would be an easy one to understand. There's add to registers. Just remember sometimes, like I think it was the out. Where's the out? Don't forget to look at this guy and see. So A can be any number between 0 and 63, but the R can only be, well, that one's 0 through 31. I thought there was one that was like 15 to 31. Was that the LI? Yeah, that was that was LDI. Has that weird that you have to subtract 16 from D before you can put it into bits.
Can you give us like a quick example of that?
So this is load immediate. So LDI, R, and now I have to be careful here, R18. If you see below R16, I can't use it. So if I put R15 here, it's an invalid instruction. I can't do R15. I have to do R16 or above.
Okay.
And then a value between 0 and 255, let's do 128. Okay.
Is it gonna be a tricky question like this in the test?
Really and truly, I've thrown one trick at this right now, which probably I shouldn't, but that's a decimal, not a hex value. But so to put this in, I have my 1110, that's E. For D, I have to take 18 and I have to subtract the low value, 16. So I'm left with 2, so I put 2 into D.
That's all fair. Another video.
It's anytime you see a range and the bottom range is not 0, you subtract the bottom range. So if you see it has to be between 16 less than or equal to D less than or equal to 31, and I only am given 4 bits, the reason for the 4 bits is I can't put a value, I can't use more bits than I have. If I was converting directly, I would need a 5th bit to do 16. I couldn't fit 16 into 4 bits. I need 5 bits for 16. So that's why you subtract here, is to fit it back in. And it's part of the instruction that they shifted over. And then the rest of it is the 128, 0, 1, 2, 4, 8, 16, 32, 64, 128. Because that time I did it decimal, I didn't do it in hex. There's no 0x there, so that indicates it's a decimal value.
Just like here, this one it was a decimal too, right? 2715.
2715, those are register numbers. They're always put in. You can't refer to them as R0X01111 for 15. You can't refer to them that way in machine language. That's part of the syntax of the machine language.
Alright, so if it has an R right there, it's in X. If no R, it's in decimal.
No, that's not what I said. 0X indicates X. The R's are register numbers, and the number associated with the register number is a decimal value. So it's R0 through R31. They never use a hex value there. They're always decimal values.
Okay.
It was a decision they made when they decided to do the assembly.
Okay. Always.
Why was subtract 18 and 16?
Why we subtract that is because this being the low value, they're representing 16 by 0. The value 0, then 17 is 0001, all the way through 31, which is being represented by 15, which is 1111. So they're basically trying to cram a 5-bit number into a 4-bit value by making the 0 value 16. And that was, again, a choice made in the hardware when they were designing the layout of the chips. They actually built that into the hardware, that for this instruction, it's always they're always adding 16 to whatever register value you give it for the.
So this might be a crazy question. So 18, well, at least in their register, in their opcode, 18 represented is represented as 2
Yes.
binary. But what if I just had 2 and it would be the same?
You can't do 2 because my register range is 16 to 31. I can't use register 2. If you see LDI R2 comma something, it should error that, but there's no way to do that. It's a restriction in the language. If I wanted to load register 2, I'd actually have to load immediate with another register and then take the value of that register into R2.
Okay.
I'd have to go through an interim step to get it into R2. Machine language is really weird that way, that sometimes you have to have a value in a certain register or it won't work. I think I mentioned the accumulator. In a lot of processors, there's a special register called the accumulator, usually called register A. If you want to do an add, one of the values has to be in that register or it won't work. There's a lot of machine language codes that do that force you to use certain registers for certain things. This processor is a little more flexible than that. That's why we don't have an accumulator register in this process. Other questions? I won't ask you a timing question on how many given this machine language, how many cycles does it take to execute? I won't pull that on you. You should be aware you can do that because it actually says in the sheet how many cycles. You take the number of cycles times the clock speed, voila, you can actually figure out exactly how much time the program should take to run when it's written in assembly with machine language. In C, they do too much other crap to really calculate. Here's a side question, maybe not associated with the test. How can you figure out how long it takes a program to run using what you know? I want to find out, I'm running this code. I've got this code. I've got main, and and I got this code, and I got this code, and I want to find out how long it takes to run one execution of that code. How can I do it without counting all the bytes and cycles? Okay, let me ask you this. What piece of electronic test equipment do we have that can measure time? Oscilloscope. So how can I use the oscilloscope plus a little bit of code to figure out how long a program takes to run?
At the start and beginning of the program, we can set something to enable and disable, and at the time, watch the oscilloscope and see
What do you mean by enable and disable?
while the program is running, I can do, if I program an output to be enabled while the program is running, and then to disable when the program ends.
Bravo. That's exactly how you can do it. Set an output pin to go high when the program, at the beginning of the program, have it go low at the end of the program, measure the time of the high square wave. I can find out down to the fraction of a second how long it takes my program to run. Very good. I wasn't expecting anybody to get that. That's a side note, by the way. That's not on the test. Again, you can sit there and look at the machine language and count every cycle and so on. I've got to see if there's actually a way, in some compilers, there's a flag, like that, what was it, vprintf flag that we use in the compiler to get floating point to work. In some compilers, there's another flag that lets you actually put in the list file, that LST file. It actually puts the number of cycles for each instruction. So you can sit there and count them and so on. So I don't know if this one has it. I know the compiler for the 68HC11 did. And I wouldn't be shocked if the GCC compiler has it. Nope. At least not by that search. It's probably in there somewhere, I just don't know it. Other questions?
Do we get any extra credit opportunities?
Well, the FLL is done. Let's see, what else is coming up this semester? There might be a couple of opportunities. I can't think of them right now. Again, keep in mind, calculators will not be allowed on the test for the beginning part of the test. So you do have to do the conversion by hand. So make sure you practice that. Best way to practice, pick a number. My numbers will not be above 255. So it'll be an 8-bit number. I'm not going to do 40, a 32-bit number on you. Use a calculator, pick a number, do the conversion, then use a calculator or the calculator in Windows in programming mode to verify that you've got the right binary, the right hex, etc.
So, calculator in Windows and programming mode?
Yeah. In Windows 10, you actually have to set programming mode for it. So normally it comes up in standard if you hit here and do programmer. Then if I want 3A in hex is 58 decimal, 72 octal, and 00111010.
BCD will be the test.
I am not going to put BCD on the test. Again, yes, computers use it. It is important, but I'm not going to put it on this test because when you get to the C-level programming, BCD is very seldom used. Is there any time you need BCD? There might be one time we need BCD this semester. If we get to it this semester. I'm not sure we're going to get to that this semester. But most of the time there's algorithms and so on to do it for you. Do you know what he's talking about? Binary
Go
code
to
decimal is using a nibble to represent values 0 through 9. So it corresponds directly to the number instead of the hex value. So you take a nit, so if I want to represent 100 in BCD, it's 0001 for 1, 0000 for 0, 0000 for the other 0. So you just make each nibble the character that you want in BCD.
Where did you start from at least?
So 0, it would be nibble 0 hex, 1 hex
Okay.
would be 100.
Like I said, what?
But no, it wouldn't be backwards.
Okay. So 1 0 0. It's in here.
Starting from left, it's 1 0
Start
0.
from the left. Okay, not the right.
But it's an easy way to have an interim point to get it to like a 7-segment display. What else?
How do we retrieve a value like memory location again? That was one of the.
Retrieving address on the address bus. Read write pin to read. If it does have a read write pin. Chip enable. Read the data bus.
I guess just to practice a lot of stuff, I guess is the best way to do it.
Well, the number systems practice, definitely. And I mean, I'll put this link up if you haven't seen. I know the guys in 3232 have seen this before. Don't worry, it won't be password protected when you get it. Still gotta fix that on my server one of these days. Let's see here. Where is it? That's the exact form of the question, other than the fact that the BCD column will be missing. The octal column will be missing. That's the exact format of the question. And then, but this is actually a way to So you can get a bunch of questions and then submit the answer, and then it tells you, hey, what did I do wrong? 101. Oh, I did 1010, you moron. Why didn't anybody stop me? But this is actually the first homework for the BCD X homework, so but it's another way of practicing. But that's the format of the question is I'm going to give you one of the number systems, you have to convert it together.
Oh, so I can go in and just do the homework.
Yeah.
Okay.
I'll put a link on there. And, you know, it lets you submit the answers. Do be aware, since you haven't used it before, it doesn't have to be your last 4 digits or your number, but if you want to go back to the same questions later, so you work them by, you generate the questions, work them by hand, and then you want to go back, you have to have the same 4 digits there, or give you different questions. It was a way to make sure everybody does the assignment, but they have to use their new number. But if you put in any number in there, it will always give you the same questions back. Unless you really if you're turning in a homework that late, well, that's just too bad. But I'll link that. Other questions?
So 2 components won't be on the test.
The only thing about 2's complement is know that high bit's a negative value.
Binary addition.
Not planned on it.
That's all I got.
If you have any questions about is something going to be on the test or something like that, email me. I'll try to get back to you. I'm actually caught up on emails for the first time in like 3 years, so that's a miracle in itself. Southall's taking it easy on me this semester. He knows I almost went batty last semester. Now I think he needs to do it for Hewitt next semester. I think he's actually going to try too. I think Hewitt's going to have a nighttime only schedule, except for senior project on Friday. But I think he's trying to make them all evening classes for Hewitt, so he doesn't go nuts.
These are senior projects. He's doing senior projects.
He's doing senior projects in the fall.
It's you, me, Ashley, Dwight, Aaron, Debbie.
Maybe a couple others. A couple were thinking about taking it this semester and then decided not to. Well, I'm still using the format, but we're still trying to come up with a consensus amongst the faculty of format and so on. Because really and truly, since I've gotten here, we've been trying to raise the bar on some projects. Not to fail students, but we got some real bad. I mean, I'm still furious. It was a team of 2 people, and they were supposed to be building a radio transmitter. And their poster was literally a bunch of components stuffed into a proto board with a wire going from the function generator to the oscilloscope underneath the proto board to make you think that it was a working circuit. And I wanted to fail their ass so bad it wasn't funny, but somehow they got a passing grade for senior projects for that crap. So They've been getting better. We had one that it was a lean project, and and it was a fake manufacturing process.